Play through a 9x9 game of a human versus alpha beta algorithm with 6 moves ahead, 3 ply. First few moves of this. I generally start in the middle. Don't really know if that's optimal or not. The strategy I normally take on 3 ply, you can kind of do whatever, but with high enough ply, you can't really beat the computer. In small moves, you can just match them fairly easily, and you just try to get an advantage around the edge. Like, this is a bad move, but put up 2 in a row along what's eventually going to be an edge, and get a guaranteed point far later in the game that way. The computer can't really see because it just doesn't go that far into the future. Alright. So, on to the code itself. So I modeled Simicago with stones, black or white, and a board, which is represented as a set of columns, lists of stones. Made it pretty easy to just add single stones, maximum number of rows, what the next stone to play is going to be, and usefully it knows what the score of this board is, which makes computing the score of next moves a lot easier. As for computing the score of next boards, what I do is I just say if I add a stone in a column to a board, how much will that change the score by? And I can just add that to the current score. A little bit faster, simpler, still messy. Adding something to a board, just find the right column to put it in there, if that column exists, yada yada. And then updating the score and the next stone and all that. Next moves, I just try every single possible place you could play and then filter down to only the values where it actually worked. So places where you hadn't hit the max number of rows yet. Okay, now onto how search works. So I have a player type, which is either a maximizer or a minimizer, and this lets me collapse down a lot of these greater than in some cases, less than in some cases, into a single case. That's what all this is about: more optimal, less optimal, mapping to max or min in different cases. So for minimax, it's just mapping the minimax function for the next player over all of the children from the next moves, and then selecting the most optimal for the current player. And minimax returns a pair of a move and a score. So that's how you can percolate the value up through different levels. Alright, alpha beta. So alpha beta is fairly similar, still just returning a move and a score. Though while you're looping, you also have to have a less than optimal bound, which is either alpha or beta, depending on who the player is. And there, if the less than optimal bound is ever more optimal strictly than the current more than optimal bound, which is going to be either alpha or beta, then we just pass through and say, okay, we're done. We don't have to look at any of the other branches. Otherwise, you go down and look at the branch and potentially update the less than optimal bound and the best move and the best score. And eventually then you just prune down to the relevant move and score.